is targeted at very basic level. So if you're coming expecting to learn, if you're an expert in the field expecting to learn something new, please don't have that expectation. I won't teach you anything new. What I hope to do is give you a very gentle introduction into the physics of Berry phases and Berry curvature in solids from my particular perspective. I recommend a couple of tutorial style type references on this topic. Charlie King has a very nice little PDF file which is really well written at the advanced undergrad, early grad student kind of range. So you can see his website, it's very easily downloadable. Also, Huanong and Hui Li in Princeton also have a very short article as well. Also on their website as well, you can find it, it's kind of nice. Also, if you're more advanced and want to dig deeper into stuff, the canonical reviews by people like Di Xiao, Chang, and Chen Yu were big pioneers in this field. It's very good, very comprehensive, with lots of stuff inside. The Nagaosa review as well is very good for Anomalous Hall effect. And also other things. You can't hear? Okay, fine. So let's do this. Start better now? Good.
Maybe you can just use the mic over there because you are actually recorded.
Oh, I'm being recorded. I see. Then I'm not going to be able to. So
yeah, you can just put
okay. So let's just do that.
You'll be able to switch. To
fine. Okay. Okay. Let's do that. Recorded. Oh no! Something happened. I just press continue. Yeah. Close it.
And then try to move.
Oh, okay. Oh, fantastic. Okay, so I'll just go up there and. Oh, I don't need this. Okay, fantastic. Bring these things up. Fantastic. Good. Right. So there are these reviews. There's also a book by Bernavik, which is kind of helpful as well. So please just have a look at it if you like more references, or come talk to me just whenever. All right. So let's get into the meat of it. Of this whole topic, we want to talk about some Berry phases and Berry curvature effects in solids, and I'll give you a really kind of small, gentle introduction to it. So we're conventionally kind of used to thinking about quasi-particles in crystals, right? So in a crystal, what happens is if I have, say, a particle in free space, it goes around, it has an energy, momentum, and a mass. That describes a particle in free space. But if I have a crystal, the energy becomes energy bands, because I have some kind of crystal periodicity. Your momentum becomes quasi-momentum. Mass, you get some kind of effective mass, and that's a very kind of nice way of describing quasi-particles or electrons, or charge carriers inside a crystal. Turns out, however, that there is another property inside these crystals, which is not just described by these conventional energy bands, quasi-momentum, effective mass that you have, that doesn't really emerge in free space. That only arises in these crystals, and this thing is called Berry curvature, right? And Berry curvature is a kind of emergent quantum mechanical property of these crystals, and you can kind of think of it as a self-rotation with a wave packet. So if you take a wave and a wave packet and you put it into a crystal, it turns out in some special crystals, in some certain crystals, that the wave packet wants to self-rotate by itself. It just wants to go around this way. So it's going to do this. And this self-rotation can give rise to a variety of interesting effects. And I'd like to tell you a bit about this in this kind of this little talk. All right. So we're very kind of used to self-rotation, and the thing is, self-rotation I'll observe and then I'll show you, enables some kind of weird transverse motion. And let me just try and illustrate. So usually, if I just take something and I just roll it down, it's just gonna, go straight down that way. So there's a little black pen here, right? Black pen, and and it's just sliding down this plank, and it's just going straight down that way, all right? It's flat that way. However, if I give a lot of kind of curvature, or not curvature, I give a lot of kind of rotation to this kind of hollow, very light kind of piece of paper, and I do this, instead of going straight flat down this way, it's going to do something interesting. It's going to curve back in this way. All right? So let's do this again for dramatic effect. Comes back like this way, right? So this is something a lot of people know about. It's called the Magnus Effect or something, and it's used in all sorts of sports, you know, like baseball and tennis. You throw curveballs, either curveballs, knuckleball, changeup, fastball, all sorts of things. What really happens is, you know, that self-rotation, you know, enables this weird transverse motion called the Magnus Effect or Magnus force. And this happens in classical mechanics, and it just comes from this thing kind of turning around. This also happens in gyroscopes, for example, as well. So what happens is, you know, you take a gyroscope, you spin it around quite a bit, it has lots of angular momentum, and it does this weird, you know, precessing kind of motion, but this force is going down this way, that's your gravitational force, but instead, you know, the gyroscope wants to precess around in this kind of direction. So, you know, that's also now a kind of a manifestation of this self-rotation enabling some kind of transverse motion. All right, and you know, the other effect is that we kind of know as well is that of Lorentz force, right? So if I have a charged particle and I apply magnetic field, say perpendicular out of the plane, and I've got this thing, what happens is the charged particle wants to go round in a circle. Okay, so that's Lorentz force, and we know this, you know, from this kind of semi-classical equations of motion that gives me kind of circular thing going around. So this gives me a self-rotation that's already inherent in the system. And then I apply some kind of electric field to the system. So now I'm going to apply electric field, and the electric field is going up in this direction, you know, perpendicular in this kind of, you know, upwards direction, vertical direction. And what happens is we get some kind of drifting cyclotron motion. All right, so, you know, this charged particle now wants to go this way. So it goes in these kind of orbits, and it moves perpendicular, mind you, to the electric field and also the magnetic field as well. So it's going drifting perpendicular, transverse to my electric field. So it's quite a ubiquitous thing in physics or in the world. So that's what happens. So I'd like to kind of like make sure that you guys understand that self-rotation enables transverse motion. And please also, if you want to interrupt me, please just shout a question out. I'd be happy to try to answer your questions. Please do that. Okay. All right. So now if we have a crystal and we have some electron that goes into it, which has some kind of self-rotation, then, you know, maybe, you know, perhaps you might expect it to also exhibit some kind of transverse motion, because now, you know, from before I gave you all these examples, you know, we can do physics by analogy. You know, maybe I will get some kind of self-rotation. So if I apply an electric field, you know, maybe it's going to move in some perpendicular direction. So if I look at the semi-classical equations of motion, I find actually there's something missing, right? So I find that this is my x dot. So that's the particle velocity, and I get, you know, group velocity. Right? And P dot, which is the force acting upon the particle, is this kind of, you know, electric field. It's a dBdx, just the gradient of your potential, and also you get Lorentz force, like I showed you from before. Okay, but, you know, it doesn't seem very symmetric, does it? But, you know, you see this big gaping hole here, and it's not quite symmetric. It turns out that actually there is some extra new term there as well, and this actually arises because these particles here going through these special crystals with self-rotation that can be described by a Berry curvature, this omega term here, can experience something called anomalous velocity. Okay? And what happens here is if say I just think of P dot here as just some kind of electric field force, right? And say, you know, that's moving in the vertical up direction, E direction. And let's say omega here is just, you know, pointing in the z direction. Let's say omega is pointing z out of the plane. It's pointing out of the plane, out of the board, just coming up this way, right? Then you'll see that if I just do electric field, you know, cross with that thing going out this way, I just get some extra velocity. So I get some extra velocity that's going this direction. And that so basically what happens is if I have a very curvature self-rotation of this wave packet, what happens is the electron experiences an anomalous velocity. It's more than just this group velocity. It's something extra, and it also goes perpendicular to the electric field that I applied. All right. So this is exactly what we said from just now. We said, we said all these things, self-rotation enables transverse motion, and so we have a particle here, which I asserted that has kind of it's going around by itself, has this orbital kind of angular momentum, and because of that, it experiences a transverse motion as well, which is perpendicular to an applied force electric field. Okay. Mind you, actually, this is it's really nice now that these semi-classical equations of motion are kind of symmetric. So you can think of Lorentz force and enormous velocity. You can see there's a duality between omega, which is my very kind of B, which is the magnetic field. I've just interchanged everything. I've basically gone from x to p or p to x. All right, so I've just interchanged p and x and p, and this is magnetic field in real space. Omega is in momentum space, which we'll talk about in just a bit. But you might think that we might get exactly the same kind of thing. But let me just remind you that previously, the trajectories that we talked about from the Lorentz force were these drifting cyclotron orbits, right? So you had this thing that went around in a circle, and it was moving, and you get this global kind of direction that's going in transverse direction. But this is quite different from that of the enormous velocity, which is just a straight trajectory that just goes this way. So it's somewhat different, but that you still get some kind of transverse motion. Very good. At this point, are you following me?
Can you give us an image of the strength of this curve?
Oh yes, so it depends from crystal to crystal, and there are formulas for it, which we'll show in many slides down. So what I'm hoping to do right now is just to give you a gentle introduction into what the phenomenology is, and just show you a bit, and then we'll try to, once you grasp the whole concept, then we'll talk a bit deeper. Okay? Any more questions?
All right.
Oh yes.
In which space your wave packet rotates? Is it rotating in a real space?
Ah, interesting. Yeah, I would say there actually is a self-rotation going on this way. So if I'm the wave packet, I'll be doing this.
Mm-hmm.
Yeah, I can do another one another time. But if I'm the wave packet, I'll be doing that.
Can you rotate in momentum space? I'm joking.
I don't know, I would have to divide myself up. I'm not so sure if I'm very comfortable with that. But yeah, okay, very good. Good, so hopefully you kind of understand this. At least on some kind of level, and we can move on. So what's the history of this, right? So there's a long kind of checkered history of this all over the place, and actually goes back way back actually to this guy called Hall. Edwin Hall actually, the discovery of the Hall effect. A few years after he discovered the Hall effect, actually discovered something called the Anomalous Hall effect, which was a large effect that happened in these ferromagnetic materials, and it was kind of like not really understood for quite a bit of time. And then there was this little paper that came out in the 50s by Karplus and Lottinger, and they proposed some kind of explanation which I will kind of outline a little bit in the coming slides. But what happens is it turns out that in certain materials, the anomalous Hall effect basically will exhibit a kind of Hall effect which is not proportional to the magnetic field that you've applied. So you get actually something that's proportional to the magnetization of the system, and as you can see here, there's a saturation of the Hall coefficient ratio or something in this kind of plot. And so what happens here is so this is kind of a long-standing problem, and people try to solve it, and people still try to solve it as well. But it's this thing. And so the role of anomalous velocity actually was kind of identified first by Karplus and Lottinger, but also by Blount as well. So let's try and understand where that kind of came from. So I'll try and give a little bit of a sketch of what Karplus and Lottinger thought about in their paper, and maybe we'll slowly get into it. Very good. So usually, as we've started before, we think again of an electron going through a crystal. Right? Electron going through a crystal. There are energy bands. There's quasi-momentum. Wonderful stuff. Right? And then you say, okay, fine. Well, what's the velocity of the electron, or this charged particle in this band? You say, okay, like I know if I calculate the velocity operator lock states, and I know this gives me this group velocity kind of relationship. And basically, this tells me that all I actually need to know about the velocity, all I seemingly need to know about the velocity of the system is to just find what the energy bands are. So if I know how the bands disperse, I basically get some kind of group velocity. And so the group velocity here, right at the bottom here, will be 0, and then I get some kind of finite group velocity here, the opposite sign there, that kind of thing. So it's very simple stuff, right? However, there may actually be some kind of interband matrix elements as well. So if I take, I'm allowed to just try anything I want. I can try, let's take the velocity operator and then take n and n prime, where n and n prime are different bands. All right, so let's say this is band n, and so maybe that's n prime, band n, and that's band n prime. And then what happens is you can kind of like calculate what the velocity matrix element is, and it turns out that there is actually a finite velocity matrix element. And then you say, okay, fine. Now when I apply electric field into the system, all right, I'm going to apply electric field in the system. Sure enough, I'm going to have my usual group velocity. But then when I apply electric field, I can actually have some kind of mixing, add mixing of this wave function here with the top wave function as well. And I can calculate this, and you can push through the calculation, and you find actually that how pops this thing. So what happens is there is some kind of interband matrix element for your velocity operator, and this actually gives you this kind of anomalous velocity kind of thing. So right now we call this omega, we call this Berry curvature. At that point, Michael Berry had written his paper yet, so they couldn't call it Berry curvature. But what happened was they wrote down a formula which is similar to this one, not exactly, but quite similar. And as you can see, it involves these kind of interband matrix elements of the velocity. All right, and so this is something that you can calculate. You can calculate this in all sorts of ways. One way of calculating it is the Kubo formula. You can also calculate the density matrix, and it goes on. But yeah, so this is the Berry curvature, and it comes actually because now I'm allowing for this kind of interband matrix element for your velocity operator. Okay, so let's think about the consequences of this now. All right, so first of all, there is now an intrinsic kind of transverse component to my current, and it gives you some kind of anomalous Hall effect, like we just said from before, right? So now my omega again is pointing out of the board, out of the plane, out of the screen. I apply an electric field that's going vertically up in the screen, then of course I'm going to get a Hall effect from this. And so this kind of explains it. So that's very nice. And the modern interpretation of this, comes from Shen Yu and Chang, and also another paper by Sundaram and Yu as well, in terms of the self-rotation of the wave packets. So understanding and calling this a Berry curvature or relating this Hauptz-Luttinger term, the enormous velocity, to the self-rotation of the wave packets was something that was only kind of realized fairly late on, right? It was only realized in the 90s-ish, and that's one consequence. And the other consequence is a little bit surprising. And so the other consequence is, I'm going to say, field bands can carry current, and that should strike you as scary. How can this happen, right? Because we know that if we just take the group velocity and we just integrate out the full band, then field bands have to be inert. They should not be able to carry the current. And this is something that we learn from solid-state physics, something that we learn from Ashworth and Mermin. And so if I just take my group velocity, integrate it out to a band from pi to pi a, and this is just for 1D band, I find actually that the current should vanish for just group velocity. But now if I add in this anomalous velocity component, I find actually that it doesn't vanish if the integral of omega over the field band actually is finite. Okay, so that means actually that if I put my Fermi energy in between these two bands and prime, I find actually that the band can carry a current. It's going to be transverse to the applied electric field, so it's non-dissipative. You can't apply the applied electric field. The current's going in a transverse direction, but it can actually carry a current. So this should be kind of striking and interesting, right? So with that, that's the first part. Maybe it's appropriate to pause for some questions before we move on.
Yeah, you constantly mention that if you apply a perpendicular electric and magnetic fields, the particle will always move perpendicularly to both.
No, to the electric field. To the electric field.
To
so
electric.
So in this part, there's no magnetic field applied. I've not applied any magnetic field. Right? There's no
But
magnetic
if you look at Earth, we always have a magnetic field, but particles don't move perpendicular to the electric field. Maybe some explanation needs to be done so that if we have small magnetic fields, we only have very small deviation from normal motion.
I see. Well, I don't consider a magnetic field. I'm a theorist, so unfortunately that doesn't play into it. But of course, you're free to include that into the equations of motion, and we hope that the physics will stand up to that. Yes.
So your equation for anomalous velocity requires electric field. There could be a transport without electric field.
I'm sorry, I can't hear you. So could you speak slower and get more?
So your equation for anomalous velocity, the one you had, yes,
This one.
This one, yeah.
Yes, very good. It's not
So
my equation.
you explicitly have electric field inside, which is because you have to accelerate your wave packets.
Mm-hmm.
But in the ballistic transport, there is no acceleration, there is no electric field. So how do you reconcile this equation with a transport in ballistic systems when there is no potential drop? Like any edge state, for example, would be of that kind.
Yeah, so I'm not discussing edge states. So this has nothing to do with edge states. I'm just discussing stuff inside the bulk. Yeah, sure. So
No, it doesn't have to be edge state. I just take a quantum wire, I apply chemical potential difference, I shoot electrons into it. If there is no any kind of disorder on the length scale of the length of the wire, I'm not going to have any potential drop. Nevertheless, the current flows, and I can see the Hall effect. So the question is there a limit on using the semi-classical equations? Because, of course, I could always shift back to full quantum mechanics and derive velocity operator directly from the commutators. I never talk about wave packets and these equations for of a Newton's second law type that tell me how the center of the wave packet propagates. So like if I play with velocity operators, I don't have any problem. But if I switch to these equations for the center of the wave packet, I have this fundamental issue that this anomalous velocity is zero in the wire which does not have impurities and potential drop if the transport is ballistic.
Yeah, that's fantastic. Thank you very much. So first of all, this probably requires an extended discussion, we could do this offline if you'd like. However, let me just make a couple of remarks. So the first remark is in a quantum wire, and I'm going in 1D. I don't know what my transverse direction is. So if I have a quantum wire and and it's ballistic, as you say, then like I don't know what the transverse direction is. So maybe this kind of stuff doesn't apply because it's just 1D anyway. But secondly, I think one can always just so obviously one can push through and use the full quantum mechanical kind of description for velocity operators and say what you do with the manipulation. But what this does is it tries to associate some kind of physical thing associated with the wave packets as we think about, say, the evolution of things. And so the intricacies and the subtleties that you talk about with regards to ballistic transport versus purity transport, some scattering of impurities is important, and that has to be dealt in a more kind of involved way, and maybe not at this kind of level. I'm just trying to give some intuition. Very good, yes. hopefully that helps.
For this picture with Berry curvature, is it important to have a gap between bands or bands I love to cross?
Very good. So one might think actually, yes, that it might be important to have a gap between the bands and the common connector or anything. But actually, the recent materials that have been shown that they actually have Berry curvature, and the bands just are there isn't a gap. And these materials are called wild semimetals and Dirac semimetals. In the wild case, they actually have some kind of Berry curvature, and it just emanates from a single wild point, from that semi-metallic point. And so yes, that's a very good question. Very good. So hopefully that was understandable, and the hope is maybe we can push on just a little bit more. Okay. So very good. So what I'll try to do is I hope I've given some kind of small introduction into anomalous velocity, wave packets, and such. And then now I'm going to talk a little bit about the Berry phase and Berry curvature, and just give you a bit of a fuller picture. All right. Thanks. So yeah. So again, we start from this thing again, crystal. There's some kind of momentum. There's Stokes Theorem as well, and we have these wave functions. And we're very accustomed to thinking of the energy dispersing with k, right? And so energy now can change the function of energy. But the block wave function can also change as a function of k as well. All right. So this block wave function can change its function of k as you move from one side of the Brillouin zone to the other. And one can ask the question, like, how are these wave functions at different points of k space, related to each other, right? What's going on there? And you can try and define maybe some kind of connection between them or distance between them by just taking their overlaps, right? So say I have some kind of block wave function at p1, and I have another some kind of wave function at p2. I want to kind of find out how they're related to each other. And so maybe the most natural thing is to kind of define some kind of overlap between those wave functions. And it turns out you can write in terms of a phase factor. And you can say, okay, fine, this is we're not sure if this is a very kind of meaningful thing, because I could just kind of arbitrarily change the phase of each of these wave functions, and I could willy-nilly change that phase factor to whichever number you want. Right, and so maybe this is not a very meaningful object. But then we say, okay, maybe just describing just one single kind of section is not that meaningful. Maybe let's take a closed path. All right, so if I take a closed path and I define that path, I find actually that the phase around the closed path is actually invariant. It's gauge invariant. As you can see here, so all extra gauges always occur in pairs. So this psi1, psi2 appears as a ket bra, and P3 here appears as a ket bra as well. P1 also appears as a ket bra. And those phases cancel out. And so the phase around the closed loop can be thought to be gauge invariant. And so this is what we call the Berry phase. And we can say, okay, fine, if we go one closed loop around momentum space, so I take a P1 and I kind of define some kind of loop, I go around it, and it turns out that the kind of infinitesimal component can be written like this, right? And then I can define maybe the Berry connection, which is some kind of phase accumulated over a small section of that path, and I can integrate that Berry connection across, a closed loop. And I find that, this gives me a Berry phase. All right, and this was what, maybe not exactly what Michael Berry talked about in his paper, but, this is what is discussed. And you can say, okay, fine, there's a Berry phase, what good is this? What can we see out of this? It turns out that it can actually manifest in some ways. So it turns out that the area enclosed, and you can see this in quantum oscillations, for example. So if I take some in quantum oscillations, might have a applied magnetic field. The particles go around in a circle in these orbits, these cyclotron orbits, and they enclose both area in real space, but also in momentum space as well. And there are particular quantization kind of rules which govern the amount of area enclosed in these closed paths. And it turns out that Berry phase accumulated through these loops that go this way, turn out here. And this actually changes the quantization of the area enclosed by these particles moving around the place. And because it changes that kind of quantization, one can ask, will this affect quantum oscillations, for example? And so in quantum oscillations, what you do is you apply a magnetic field to your system, right? And you measure some quantity, like rho xx, like your resistivity or some magnetization in your system. And what you do is you see as a function of magnetic field, your rho xx actually oscillates with magnetic field. And then you can ask, how those oscillations look as a function of magnetic field. So it turns out that these people, the Kim group and also the Guy group, were able to measure the quantum oscillations in graphene. It turns out that graphene has a pi Berry phase, and that pi Berry phase should also turn up should turn up here as well in this gamma factor here. So it turns out that this cancels and becomes 0, and it turns out that the Berry phase comes up as an intercept of this Landau fan diagram, which show the quantum oscillations. So if you compare, say, the graphene kind of quantum oscillations versus that of graphite, you find that the graphite, intercept goes to 0, so there's 0 Berry phase, and here the intercept goes to kind of half the units of 2 pi. And so by using quantum oscillations, one can kind of see the Berry phase, and so it turns up in actual measurements. And this should come across to you as a little bit surprising, is because we always taught that observables are basically eigenvalues, or can be expressed in terms of eigenvalues of some operator. And the Berry phase is not quite an eigenvalue of an operator we can define, and so this is kind of neat, I think. All right. So now that we've established that the Berry phase is some kind of something real that can be seen in experiments, we can say, okay, fine, what does this kind of remind you of? So this may remind you of, so this is kind of like a shift, right? A shift in intercepts. It goes from 0 to something like half. So what does this remind you of? This kind of reminds you of a little bit of the Aharonov-Bohm phase, the AB phase. And what happens when you take a charged particle and move around in a magnetic field? It closes a space and picks up the phase. And this can actually shift your electron diffraction patterns. So Aharonov-Bohm kind of propose this. You apply a magnetic field and you create some kind of, and you make sure the magnetic field is confined to this solenoid, and outside it you don't really have any magnetic field. And now you try and change. You can shift around your electron diffraction experiment. So you can have a source, which I've taken from the final lectures, and usually you get this kind of double slit type interference pattern for your electron diffraction. But now when you apply a magnetic field, just inside here, only enclosed inside your solenoid. Outside of it, no magnetic field. It turns out that the acquiring of this AB phase can shift your diffraction pattern up or down, depending on your magnetic field that you've applied, or the vector potential that you've applied. So it's kind of dependent upon the AB phase that you've enclosed in this path. So this, as you can see, it's kind of a closed path here. And so this shows that this is kind of neat. This looks, because of this closed path kind of thing, looks very similar to the Berry phase. And you see, okay, fine, maybe this is kind of similar to each other. And so it turns out that that you can compare them. So the AB phase in one, you pick a phase because of the magnetic field, and you look at charged particles going around in a closed loop, and that gives you an AB phase. Berry phase, same thing as well. This is real space. This is momentum space. Now I've taken the wave function that I've gone around a loop. It picks up some kind of very phase. And that's also something quite similar. In this case here, it depended on the magnetic field. All right, so you might think, okay, maybe I can try and think about some kind of effective magnetic field, but in momentum space for this very phase thing. And it turns out that by going around this loop, I can use Stokes Theorem. You remember that this looks a lot like Stokes Theorem. And then I can rewrite this as a curl of this A, this Berry connection. And it turns out that this is the Berry curvature. So I can think of actually Berry curvature as some kind of magnetic field, but in phase-space, momentum space. And it's piercing right through this thing, so much so that particles which go around one loop of this, will pick up a Berry phase. Right, so that's very good, and this kind of gels into our understanding from before in the first kind of introductory section about anomalous velocity and Lorentz force. So there's kind of this duality, if you would, between magnetic field and Berry curvature.
Question.
Yes.
So you emphasized that you emphasized that the anomalous velocity comes from the interband matrix elements. And now you sort of explain it from a very different point of view. What is the...
What gives? Yeah, what gives? So yeah. So that's amazing, and so that's very good question. So when Kalbus and Luttinger kind of looked at it, they wrote down this nice formula or something, and you can see it. It turns out after some fancy footwork, you can write down all sorts of things. You can actually make that interband formula look like an intraband formula, and we'll talk about this afterwards. So it's all good.
But just to make sure, this UPs, they are from the same band.
From the same band, yes. So you would think, okay, you might think that these two things are disjoint and disconnected, but they're not. They're not actually disjoint and disconnected. And as we will see, this is a kind of mildly important thing. Any more questions? Hopefully, I haven't lost too many people. Okay, very good. So let's move on. So where was I? Yes, okay, so magnetic field and Berry curvature are kind of dual to each other. I can think of, Berry curvature as a kind of magnetic field, but in momentum space. All right, so let's move on. You can see, okay, find this nice kind of duality between them. I've exchanged X and P and omega and B. This was B of R, omega of P. All right, though it's not written down here, and so that's kind of nice. But does this duality kind of extend further? And it actually does. So in a magnetic field, what happens is you can define what happens is your velocity commutator, your velocities don't commute, and your Vx and Vy don't commute, and I can relate that to my magnetic field applied in the z direction. All right, and I can see this by some kind of simple kind of minimal coupling, right, or Pauli substitution, and so I've gone from P to P minus EA over C, where A was the vector potential that we're kind of familiar with from Maxwell's equations. You say, okay, fine. Berry curvature sounds like a magnetic field, but in this momentum space. Does it do something else as well? Oh yeah, it does. So I've just interchanged P and R or V and R, and now actually it turns out that this position thing doesn't Rx or Y don't commute anymore, and it doesn't commute up to this Berry curvature thing. And again, there's also some kind of modified Pauli substitution, modified minimal coupling, where R goes to R minus EA, where A is the Berry connection. So I've changed big A, vector potential, to this curly A, Berry connection. This is in real space R, and this is in momentum space P. Right? And you can, by doing this simple substitution into your equations, you can already see that this kind of produces this commutation relation as well. So this duality is kind of pretty deep, and more details can be found in these papers. Right, very good. So with that, we kind of like exhibited the kind of general properties. So I thought maybe we talk a little bit about two-band model to give you a bit more flavor. How much time do we have?
What's it? Another 15 minutes plus questions?
50 minutes. 15. That's all I have left. To talk or to?
20 minutes.
Oh, 15. That's maybe 15 then. Then I'll rush through a bit quicker. I'm sorry about this. I didn't take time. So one can try and see all of this in an example two-band model, and you can see this in kind of graphene. So graphene is a hexagonal lattice, and there are these A, B sites here, and the Hamiltonian can be written in terms of this kind of form, where the top and bottom here tell me the weight of the wave function on either the A and the B sides. So because it's some kind of a two-band model, I can kind of describe it in terms of a spinner in a Bloch sphere. So there's a spinner in the Bloch sphere, and it turns out here, if we just do the calculation, this gives us the pi Berry phase that I told you about. You can kind of see it straight away already from the wave function, the spinner type wave function that I put up there. But this pi Berry phase is the same for all momentum states, all the way up. So if I look at the Berry curvature is vanishing. So so it's not going to be there. But we can actually gap out graphene, at least in our minds, and we can add some kind of AB sublattice asymmetry. What happens is this kind of cat-sounding spinner from the equator, and I get something in some kind of north or south hemisphere. Right? So for example, here, if it's pointing the North Pole, it means it's everything on the A side, for example. And so now my Berry phase changes as well as the function of momentum. If I recall the Stokes type formula that I wrote down from before, the Berry curvature is just this simple formula. Right? So it's just this p squared delta over some p cubed. Right? So one can show this from both the Stokes type formula, but also from that interband thing that
So if I come back
yes.
If I come back to the magnetic oscillation,
Yes.
The path of the oscillations will remain pi, but here you already don't have very fast pi.
Yes, that's right. So this will change. So everything that I talked about from before, the quantum oscillations thing, is for pi Berry phase alone for graphene. This is gapped graphene with a delta as well. There was some AB sublattice.
But gapped graphene has still shift of oscillations pi.
But it will change. It will change a little bit. Oh, okay. So
Different.
it will change. Change a little bit. But let's move on. I don't think it's very pertinent to our discussion. That's our net Berry curvature. I can also rewrite everything in terms of some solid angle swept. So this is kind of a useful thing. So you can think of the Berry curvature as the solid angle swept by this wave function vector, this d vector of my Hamiltonian. And so this whole thing here is the net Berry curvature, and the Berry curvature can be thought of as, for a simple two-band model, you can think of it. It's only in this two-band model that you have this. So it's you can think of your Berry curvature as some kind of solid angle density, right? How will I get this Berry curvature in these systems? It turns out that there are very strong constraints in Berry curvature, given by time reversal symmetry and inversion symmetry. If I have time reversal symmetry, this happens. If I have inversion symmetry, this interchange has to occur as well. And I need to break one of them, at least, to be able to get some form of Berry curvature. And it turns out that in the gapped graphene case, we broke inversion symmetry. And so that, in value k and k prime of graphene, so graphene band structure comes in two spots, k and k prime of your Brillouin zone, and you basically get plus and minus of your Berry curvature in either one of them. And this was, so I will skip this. This was recently seen actually in the transition method by Caltronics, which can be thought of in a simple way as gapped graphene. And what they did was they shone circularly polarized light, and they kind of excited particles in k or k prime, left and right hand kind of circularly polarized light, and then they kind of measured Hall effect. They found that they could get a Hall effect which was tunable by your photoexcited carrier density just by pumping, and it was at zero magnetic field, and this came from Berry curvature. All right, so that's one very simple thing one can do. What I wanted to do right now in the remaining 10 minutes maybe-ish was maybe kind of talk a little bit about what these field bands are and kind of give you some context. Okay, very good. So there's this thing, the 80s, a number of people were able to see quantization of the Hall effect. It was called the quantum Hall effect. It was quantized on these plateaus, and it was quantized to units of h over e squared, which can be used now as a kind of a measurement standard. So the Hall effect again is you apply electric field, you get a current, and you try and get this whole ratio out. Right, very good. So how does this have to do with Berry curvature? So it turns out that, if in a simplistic kind of way, I can think of Berry curvature for an entire filled band. I need to kind of move my d vector, my wave function, all the way through the whole sphere, this block sphere. And it turns out that wrapping across this whole sphere will give me a fixed total solid angle, which is 4 pi. And so if I now kind of integrate out the Berry curvature for a filled band, I get some kind of quantized Hall connectivity. And one might think that, given this kind of simple kind of argument, one might think that this explains that might be related to the quantum Hall effect. And there are also very many other faces to the quantum Hall effect which are very important, including edge states, and also flux threading, called Laffin. And it turns out that Thales in the 80s thought about this. And he tried to write down this interband formula that you pointed out. He wrote this down, and after some fancy footwork, he was able to show that this thing, was indeed just a kind of Berry curvature. But I don't think he called it the Berry curvature. And as we argued from just now, it just comes around from this wrapping of this entire sphere, the solid angle, 4 pi. And it's really nice because it's important for applications in topological pastries. So as you can see, there's a big difference between the bagel and the cinnamon roll. It's very important, so much so that the Nobel Committee had to talk about it. And in just a couple of days ago, the Nobel Prize was awarded to Dallas, Haldane, and Kosterlitz, partly for understanding how these topological things, the wrapping of spheres. So the wrapping of the sphere is really a topology explain the quantum Hall effect, and also other things as well, right? So that's very good. Haldane was also kind of involved in this kind of thing. He got his part for also other investigations into quantum spin chains. But also he wrote this very nice paper about a zero field quantum Hall effect, or zero magnetic field quantum Hall effect, what we call a Chern insulator. And instead of breaking inversion symmetry like I did, in this gap between case, in transition method like Kalkschmidt's case, he wrote time reversal symmetry. And he wrote down a full kind of type binding graphene type model with second neighbor hopping, which were complex, and was able to show that you were able to get the mu equals to 1 and mu equals to -1. These are filling fractions, or e squared over h, or minus e squared over h in your quantum Hall effect, type of thing, even without applying any kind of magnetic field. Right? And this is very nice, and he wrote at the end of his paper that it's kind of interesting. This he thought it was kind of unlikely to be physically realized. But interestingly, just a couple of years ago, in fact 2 years ago, these people, Estlinger and Jotsu, were able to try and recreate the Haldane model in a cold atoms kind of setting. They were able to kind of measure the Berry curvature encoded as well by using their cold atoms measurement. And even more, there was also a recent experiment by Zhang in Treizhu Zhang in China, Beijing, where they tried to create this quantum anomalous Hall state in a magnetically doped TI. And they were able to see, as you can see now, sigma xy, that sigma xy on the y-axis, kind of quantized to e squared over h. And this was at 0 magnetic field. And so this was kind of nice. That's that. So I just want to say that Berry curvature is that enough time? Good? 5 minutes. Oh, okay. So Berry curvature is fun. All right. So I hope to have kind of impressed that upon you. That Berry curvature is fun, and there are lots of people who think about it or effects associated with it. It's a fairly long laundry list of things, and this is clearly non-exhaustive. Right? I'm missing a lot of things right now. It's just some things that happen to catch my attention. And there are lots of people who worked in the very traditional anomalous Hall type stuff. Spin Hall, value Hall, lots of people involved in this kind of stuff. But there are also people interested in how Berry curvature relates to polarization, charge polarization in insulators, as well as orbital magnetization. There's people interested in optics and how it relates in optics as well. You can get shift photocurrents, weird, optoelectronic effects in these materials, also interaction effects, to try and understand how this modifies Fermi liquid theory. So I have a Berry curvature in my system, does this change my understanding of what Fermi liquid theory is? And there was a very, very beautiful paper by Dan Zon about this. It's amazing. There's also new kind of anomalous transport stuff that happens in these materials that go beyond just anomalous Hall type effects. So apparently Berry curvature is related to interesting effects like the chiral magnetic effect and chiral anomaly effect in these wild stone metals. And they can be seen in a variety of ways, including via negative magnetoresistance. So there's been some activity recently experimentally in that front. And we just try and end off with this. Berry curvature exists in a lot of materials, or are related to a lot of materials, the topological insulators, or for example, the magnetically doped topological insulators have this quantum anomalous Hall state that Haldane talked about from a long time ago. But the rest of them also kind of have some relation to what we just talked about. They also have these interesting kind of edge states at their boundaries. But there are also these very, very, very new materials, 3D Dirac and wild stone metals, which turns out that each of these wild nodes are sources or sinks of Berry curvature. And so you can think of them as like a point source. Each of these, wild points, a point source of Berry curvature, and Berry curvature just emanates from these points. And a lot of the physics, of the interesting physics like the chiral anomaly and the chiral magnetic effect arise quite simply actually from considering the Berry curvature emanating from these points. So a lot of interest in these materials right now, and also in these 2D Dirac materials that I talked to you about. If you gap it, if you gap the Dirac system, for example, in this transition metal like calcinite, or gapped graphene, or dual gated bilayer graphene, where you apply an electric field perpendicular to the two layers. They also host Berry curvature at different hot spots in brittle and zone. And so, trying to manipulate those things is also very interesting. So with that, I think I'll end. Thank you very much.
Questions already been asked?
Can you answer the question about two different views on these effects? First, we have Berry curvature obtained from many levels, and the second one we have Berry phase obtained only from one band.
Yeah.
How does it correlate?
So basically, I kind of skimmed over this. I didn't really talk about this, so sorry about that. But basically, I said there was some fancy footwork. So to go from this formula to this formula, this is in a single band, takes a bit of algebra. Just uses a couple of identities, you push through. Turns out that DHDK interband can be related to you can write down epsilon n minus epsilon n prime, and then you get a partial of one thing. It's a little complicated, but suffice to say that it's here. It's in this step here. So one can show that this formula actually formally becomes this, and they're related. So you can think of this actually as this is actually quite interesting. You can think the bands are kind of you might think that bands are not related at all. N and M prime are just some unrelated distant cousins that don't ever talk to each other. It turns out that because you can go from here to here, there's a constraint that kind of makes them related to each other. And Berry called this the effect of Berry phase kind of physics. How the universe is acting on me. On this object. So this is you're trying to find out how the rest of the bands of the universe is acting on the single band. And there is this kind of constraint. It's kind of special. I hope that helps.
I could also maybe quickly add, so for example, if you solve some kind of quantum kinetic equation, of course the off-diagonal elements describing these interband transitions coupled to the diagonal, so you could express off-diagonal in terms of diagonal. And plugging back into the equation for the diagonal elements of the density matrix. Everything at the end of the day could be written in terms of just the diagonal elements of the density matrix. So they're coupled. So in any kind of theory, quantum kinetic theory, the off-diagonal and diagonal, the intraband and intraband density matrix elements in the cup. But I guess.
Yeah, no, when you're technical about it, we can talk about those off-diagonal ones. There's also kind of, yeah. Okay, yes. Hopefully that helps, yeah.
First, in the beginning you are talking about self-rotating of weight pair. Does it mean that the electrons in crystal have additional magnetic moment, or and therefore they have additional energy in the magnetic field?
That's a beautiful question. Yeah. So I think the answer is yes. There is an orbital contribution to magnetic moment in these systems, and that can give you also some kind of Zeeman effect, for example. A magnetic field, couple it, and these people talk about it quite a bit. So these people here, but also these people here.
Okay, and then the last question. So there is a ІВТ formulas about magnetic moments of a band in so the energy or magnetic moment of a band, and does it correlate with your calculations?
I'm sorry, I don't know the ІВТ model.
Oh.
Yeah.
Thank you very much. It's a very nice talk. And you only briefly mentioned some magnetic materials in Anomalous Effect.
Yeah, very briefly.
And yeah, and the rest to me like focus on some. To me is what is exotic materials. So would you expect any changes of your formalism if I would like to consider a magnetic system? Because you talk about the importance of like applied fields, band mixing and stuff.
I think there might be some changes, that you have additional terms in the Hamiltonian, you have to include these things. I think maybe the methodology of trying to address these questions could still apply. And in fact, actually, these people, these Xiao Xinyu, are interested in these materials as well, these magnetic materials, and they try to address these things. So I think it can be applied with the same methodology. I'm not sure if the question, the formulas that I wrote down will be exactly the same. Of course, there are going to be some changes as you change material to material, because the Hamiltonian is going to change. Additionally, on top of that, when you apply a magnetic field to these systems, as we just discussed just now there, about this omega and B, you can actually get weird things happening as well. So you can actually pump, one charge to one flavor to another flavor, as well in these wild signals. So new and weird things can happen. The commutation relations, for example, Vx, Vy, and RIRJ, those things are no longer the same anymore as well. Those get changed as well. There are additional factors that appear, and one has to consider those things.
Thank you very much.
So let me ask a quick question.
Thanks.
Your talk was based exclusively on an idealized and perfect crystal chip. Maybe you could add some comments on how robust this attacks against disorder. Or what changes if you do have disorder? At which point you have to start worrying about disorder?
So if you're inside the gap, I think you don't really have to worry so much about disorder.
So for this quantized effect.
So, yeah, that's why the quantized effects. So
things like anomalous Hall effect.
So for the quantized anomalous Hall effect, for example, in these Chern insulators, then I don't think actually disorder should play a particularly big role or any role actually in these gapped materials where your Fermi energy is inside the gap. It may play some role in terms of seeing the phenomena to get kind of quantized plateaus. It's very important to have those things there so that when you tune the Fermi energy via magnetic field or by gate potential, those states have to pin your Fermi energy. But in terms of what the Hall effect is, I don't think those will change inside the gap. Outside the gap, I think it's anybody's guess. At least for me, I think one has to do the calculation, and I don't really know how it changes that.
But you don't want to add any qualitative remarks to that end?
So I'd rather not get into it because it's a kind of a
it's complicated.
It's complicated and it becomes it gets a little involved. There was a long literature treating this. It's
going
very
back to the
colorful.
anomalous color fact, because it's a mess in general, right?
It's very colorful.
The very curvature, but also skew scattering, side jumps.
That's right. Skew scattering and side jumps and all comes together with the zoo. Yeah, that's right. So it's complicated and one has to be careful about a lot of things. I think there are lots of experts in the audience that can better kind of answer those questions.
Right. Let's see.
Yes, I would like to come back to this question which was already asked about the rotation of the wave packet, and I'm trying to think, is it possible to understand it in some simple ways? For example, if you have two-dimensional square lattice, and you think about wave packets in this case, and the bands are very simple, is it possible to explain how will you, maybe describe this rotation of wave packet? How will you see? Suppose you have a microscope, a magic microscope, which sees the wave function. How will it look under this microscope?
I'm sorry, I don't have an answer to that microscopic question. It does have a magnetic moment. So you can image this, and recently people have tried to do this. So there was a recent paper by Kim-Fai Mak from Penn State, where they take one of these transitional dicalcinites, they apply electric field, they accumulate electrons in K and K prime, and there they can see that there's a curve rotation to each. So you can see this experimentally, and you can also calculate it as well. So Chang and Yu and Sundaram and Yu also calculate what the wave packet rotation is, and you can actually explicitly see it in those calculations. But I thought this was an advanced topic that we're not covering.
I have a question. The first question actually concerns the gap system, and you showed us, for example, that for one valid degree of freedom in the gap graphene, whole conductivity is proportional to integral of Berry curvature. Yes, and you showed us the formula where Berry curvature is proportional to gap. My question is, what happens when gap goes to zero? Is conductivity zero or not to zero? Because it's just topological.
Okay. No. So it turns out that there is some Berry curvature, but it's all concentrated, at the Dirac point. So so there's zero density states there. So
conductivity is not zero even in the limit when the gap goes to zero.
No, I didn't say that. No, I didn't say that. No, so let me go slowly. All right. So it turns out. Okay. So two steps. All right. Step number one. All right, delta goes to zero. Where's the Berry curvature? It's zero everywhere else except at the Dirac point. Except, so it's there. Wait, yes. And then step number two. It turns out there are zero density states there. So there's no way to get anything out of it. So you're never there, and there's also zero density states there. So it doesn't contribute at all. So the answer is sigma xy is zero.
Even for one valley. For one spin or one valley, zero.
I would think so. I would hope so, yes.
And the second question is, we showed analogy between Berry connection and the usual vector potential, which is also called a connection in physics and mathematics. Yes, and we know that usual vector potential can depend on time, and in principle we have kinetic term for it. What would be dependence on time for Berry connection and maybe kinetic term for it? Is it possible to have such situation?
That's a very interesting question. I have not thought of that. I don't know the answer to that question. Maybe. I don't know the answer to the question. I'm sorry. I've not thought of that. But yeah, maybe, possibly.
Can I ask one more question? So, So currently we see mostly models with conductivity with only one band. But if you consider having all the different bands we have in a normal material, do effects of Barry curvature have the same sign in each band? How the topological currents add up from each band?
Yeah, you just add the topological currents in each of the bands. And
but do they have the same sign, or
it depends on material. So you have to look at the specifics of the thing. I can't make any generalized statement.
But they have to add up to 0.
Oh, they all have to add to 0, of course. Yes, that's right. So if I take the whole universe at 0, but if it's just one single band, it's partially kind of filled. Yeah, but yeah. So that's a very good point. Yes, right.
I'd just like to make a comment, actually it's sort of an answer to Yaroslav's question, I think, about the anomalous Hall effect, what the impurities are. So, of course, as Justin said, this depends a lot on the details of the particular material and the kind of spin-orbit coupling and so forth. But a very interesting case was discussed at some length by Nozier and Levina a number of years ago, and in which you have a Rashba spin-orbit coupling and just sort of potential scatterers. And the amusing thing there is that, first of all, you can try to measure the anomalous Hall effect two different ways. And there's two principles. One is you could put an AC field on, so you don't need any impurities. Of course, if you don't have impurities and you put a DC field on, then the current is just going to run to infinity. It doesn't make sense. But you can put an AC field on, and then the anomalous, then the Barry curvature term is the important thing, and you take it into account, and you would get the right answer. It's a little subtle because there's the anomalous velocity, and there's also a dipole moment, which are exactly equal. So there's a factor of 2 enhancement over what you would get if you just considered the anomalous velocity term naively. When you put, on the other hand, if you use when there are impurities, what you find is that the Hall current is opposite in sign. You get something which is equal in magnitude but opposite in sign. So in that case, obviously the impurities are very important.
Thank you. So, any other urgent? Okay, a whole bunch of questions.
I have a very simple question. Consider we have 2 electron systems, one with a Barry phase 0 and another traditional, one with a Barry phase non-zero and another traditional simple electron system with a Barry phase 0. Are there any restrictions in the electron, in terms of electron transfer? That means experimentally, if you have a contact with a Barry phase material and a simple metal or a tunneling contact, are there any restrictions on the electron transfer, or in other words, are there any Barry phase conservation laws or something like this? Thank you.
Unfortunately, that isn't a simple question. So I don't have an answer for that. So I don't know. I don't know. Maybe, but I don't think so. But one has to calculate it. So that's an interesting question. Maybe you should do the calculation. More questions?
Can you show us this figure with the Hall effect in MOS2?
Wait.
So in the gap of that MOS2, the Hall effect is 0.
Yes.
It only comes from the valleys where the Barry curvature is non-zero.
Well, yeah. No, you need the photo excite, right? So the valley K and K prime cancel each other out because it's plus and minus, right? On top of that, it's kind of close. So you have to now photo excite so that you can imbalance the values k and k prime, so as to try and get some kind of Hall effect.
So what I'm trying to compare is that we also had this discussion of Berry curvature in gap graphene. So in gap graphene, the picture looks exactly the same. There are these two valleys and the hot spot with the non-zero Berry curvature is at the bottom or the top of the valleys. And if I calculate the sigma xy valley connectivity for one valley, I will get the non-zero value which comes from those hotspots.
That's right, and even inside the gap. So even
even exactly. And I've even seen a calculation we did when I plotted the integral, and I see the integrand kind of cancels out until I reach the hotspots. And then at the hotspot itself, it jumps to quantized value, and then it remains quantized in the gap, because in the gap there are no states, so the only quantized value can come from this, from this value. But then the issue is that eventually that quantity that is calculated is not observable, because nobody can measure sigma xy value.
Ah, that's a very interesting point.
So what is measured is the non-local resistance in this multi-terminal experiment.
Yes, that's right, that's right.
And that non-local resistance turns out to be non-zero exactly in the middle of the gap, where there are no states. So like these two things are kind of easy to reconcile in quantum Hall effect, because they are edge states. But in this system there are no edge states. And so like that non-local resistance being non-zero in the middle of the gap, and that non-observable sigma xy value Hall being basically quantized, but not directly related to that, because it's not possible or easy to get non-local resistance at some distance from the gap system, because there is gap, so the electrons cannot go across 1 micron. So in other words, what I'm saying is that I did the calculations. If I try to calculate non-local resistance in a real graphene bridge, which is as many microns as you want long, I always get zero non-local resistance. There is no non-zero local resistance coming from that sigma xy non-zero value Hall connectivity. So there's some kind of fundamental problem in this specific case of gap graphene, that this Poole formula or Berry curvature calculated in that sigma xy value, which cannot be measured directly, eventually is difficult to reconcile with the directly measurable quantity, which is that resistance in the gap when there are no states.
Thank you very much for your comment and for your question as well inside that comment. So just for the education of everybody, sorry I don't really know your name, but our colleague here talking about non-local experiments that were done by a number of groups in Manchester, Tokyo, China, where they tried to measure these kind of Berry curvature effects from each of these valleys. It's called the Valley Hall effect. And they see signals, actually, they see real signals in a variety of systems. Gallium nitride graphene, they also see it in graphene or nitride, and they see non-local signals. So what happens is the charge-neutral mode composed of K and K prime propagate throughout the system, and we get some kind of mediated by charge-neutral mode, kind of non-local resistance measurements in these materials. We apply some current, where some voltage. There are definitely issues and concerns with regard to that. So people thought that maybe edge states were involved in these systems, but the edge states aren't very robust, and the Chinese group was able to show that it didn't really depend on the edges, and there was also very sensitive measurements and kind of analysis by the Tokyo group, the Tokyo group as well, which kind of showed that it came from the bulk. And frankly, understanding what it is that's being transported is actually the topic of current research. So
you're implying some collective mode.